Hey guys, today we're going to be talking about more types of regression and how to find the best regression models. So for this one, it's talking about mammals and other warm-blooded animals trying to stay warm, and it requires energy. So it talks about all of this stuff. Basically, what we're looking at is the body weight of a warm-blooded animal in comparison to its pulse rate. So I personally, I don't know, I know that it's nice to know what animal we're looking at, but I don't really like having words in the first column just because it kind of gets confusing if you have too many columns. So I'm just going to cross that out and I'm going to write L1 and L2 so I know where I'm entering my data. The next weird thing, though, that you probably haven't seen before is it wants the power regression model. So that's just like a new type of function that I'm going to show y'all, and we're going to find that regression model and go from there. So I'm going to go ahead and get my calculator set up and ready for regression. The first thing that I want to do to get it ready is I'm going to hit second 0 to go to catalog, and I want to turn my diagnostic on. So I'm going to hit the inverse button to take me down to the D's, and then I'm just going to scroll down a little bit until I get to diagnostic on. And okay, almost there. We're gonna get it. Diagnostic on. And then I'm gonna press enter again so that it says done. And the next thing I wanna do is turn my stat plot on so that I can see scatter plots. So I'm gonna go to second y equals, click on the first one, and just turn the plot on. So I press enter on for that one. And now I'm just gonna go back to my regular screen, or it's gonna go to mode. Okay, so I'm gonna go back to my regular screen, and I want to enter my data now in L1 and L2. So I'm gonna go to stat and click enter on edit, and we have L1 and L2. So I'm just gonna go ahead and enter this data. And I'll pause it so y'all don't have to watch this whole thing. Alright, so now I've got my data entered and I want to go back to stat. And then this time I'm trying to calculate regression, so I'm going to go over to calc. And we want power regression. So you're just going to scroll through here until you find power. And it's right there below exponential. So it would be A if you were to click on it. I always just scroll down to power so that it doesn't mess up when I'm trying to click it. So I'm going to choose power regression. And I have L1 and L2 in there just like I want. For store regression equation, I'm just going to go to vars and over to yvars and press enter to get y1 in there. So now it'll put our equation into y equals for us. And now I'm just going to hit calculate. And this is what it gives me for the power regression model. So I'm going to go ahead and copy this over real quick. Okay, so now I'm just going to look at the base equation that it gives me and copy my equation down. So let me actually, I'm gonna move this up a little bit so that I'll have room to write B, and I'll move my box up. Okay, I don't know why it changed into a funny shape for a second. Anyway, it doesn't matter. So now I need to write my equation. So the base equation for power models is going to be y equals a times x to the b. So it's kind of like exponential, except your x value is what's being raised to a power. So it's also kind of weird. But we're going to go ahead and write the regression model. So it says y equals a is 231.2 times x to the b, which is negative 0.297. So that would be our regression equation. And it says that the r-squared value is 0.9766, so that's pretty good as far as it's a pretty good fit. So now I'm gonna use the model, which just means use my equation, to predict the pulse rate for a 450 kilogram horse. So first off, I want to say 450 kilograms is a lot bigger than any of the other weights that we have in there. So it might not be a super accurate number, but we're going to go ahead and predict it anyway because it tells us to. So the equation, if you were typing it in, would be 231.2 times 450 to the negative 0.297 power. So now I'm going to do a couple of different things on the calculator. The first thing I'm going to do is I'm going to hit zoom 9 and just look at what our graph looks like. So this looks like the pulse rate is going down pretty rapidly and then starts to level off as the body weight increases. So then I want to see like where the pulse rate would be for a 450 kilogram horse. So instead of trying to like find 450 on the graph, instead of trying to plug it in, I want to find it in the table, but I don't want to scroll down 450 times. So I'm going to go to second window, and that'll take me to table set. And normally table start is at 0. I had already entered 450 in there so that I could look at it. But if the table start is 0, you're just going to want to change it to 450 right here, just for this problem. And so then I'm going to hit second graph so that it'll take me to the table. And 450 is my X value, and the Y value, or the pulse rate that we're looking for, is 37.698. So coming back in here to answer that question, it's 37.698, and it's beats per minute is our unit. So that takes care of that problem, and that just kind of goes over the basics of power regression. Okay, so now we're going to do another new type of regression equation, which is logarithmic, which you may have done before. It's a pretty common one, but we're going to go ahead and go through one so that you can see it at least once. So this one is talking about life expectancy in Americans from the year 1900. So it wants me to find a logarithmic regression equation to fit the model. And it tells me that 1900, they want you to use year, or not year, but they want you to use x equals 1. 1910 would be x equals 2, and then so on for each of the decades. So I'm going to go ahead and fill those in here. So it goes from 1 to 12. And so then you're going to want to enter all of this in L1 and L2. So the years, with the way they have it split up, L1 is going to be the first and third row, and L2 is going to be the second and fourth row. So I'm going to go ahead and start working on that. So I'm going to go back to stat and edit again. And then this is just something I didn't show you in the last video in case you wanted to see it. If you just scroll up to L2 and press clear and then press enter, then it'll clear out your list for you without deleting L2. So that's the way that I always do it. I know that there are other like methods of doing it as well, but that's just how I normally do it. So I'm going to go ahead and enter that data now. Okay, so I've got all of that data entered in 1 through 12, and then all of the numbers for L2 as well. And so now I'm going to go back to stat, and this time I want to go to calc. And then if you look down here, number 9 says ln reg. So for logarithmic, you would choose ln, and that's the natural log. So that's just something to try to remember. You're choosing ln reg. And then, so I'm going to just hit 9 instead of trying to scroll down. And I've got L1 and L2. I'm going to skip frequency list, and I'm going to store my equation in Y1. So I've got all of that set up, and now I'm just going to hit calculate. And it gives me the equation, and I'm going to go ahead and put that in the notes. So I'm going to go ahead and write out our equation now, and then if you guys get stuck and you can't remember like which one is logarithmic, you can always come back to the notes here, and I guess it won't let me write on that, or maybe I'm not writing anymore. Okay. And choose the ln. It shows it at the top of the little screen. And so if I write out the logarithmic regression equation, then it would end up being y equals A, which is 42.53, and then it's plus B, which is 13.86, and then times the natural log of x. So that's how I would end up writing that out. And then for number 2, it wants you to use the model to predict the average American life expectancy for the year 2030. So we went all the way up to 2010, so that means that 2020 would have been 13 and 2030 would just be 14 in terms of x. So I'm just going to write x equals 14. And then I'm going to go to 14 in my table. So I'm going to come back over here. And if I look at the table right now, we're still going to be at 450 because that's what I put in a minute ago. So I'm going to go back to table set, and since I want 14, I'm just going to enter 14. And then hit second table again. And I see that the life expectancy in 2030, it's predicting to be 79 years old, or 79.1. So y would be 79.1 years. So that would just be an example of logarithmic regression. Okay, so now we're going to look at one that it's talking about a manufacturer of seals for industrial equipment tests samples of its seals at a variety of temperatures and collects the data. So it's measuring how many seals fail based on what temperature it is. So the first thing it wants you to do is create a scatter plot of the data. So I'm going to come back to my calculator, stat edit, and I'm going to clear my 2 lists and then enter the new data that it gave us. And also, while you're doing this, just to have everything, nice and pretty for you whenever you want to do your new scatter plot, I always come over and clear out Y1 as well. So also, again, I know there are different methods of doing this. That's just the way that I do it. If you have a different method, that's okay. So I'm going to go ahead and enter this data for us. 1 second. Okay, so all of our data is in L1 and L2, and it just wants a scatter plot, so all I have to do now is press zoom 9. And this is my weird little scatter plot that I'm going to go ahead and copy over. So here's my scatter plot. So for part A, I'm just going to draw an arrow to show that this is my scatter plot. And then on part B, it's asking you based on the shape, you're trying to predict what type of regression could model the data. So what type of function does it look like? So based on that, you can't tell a whole lot. It could be several different things. This one dot down here is kind of throwing a lot of stuff off. So I'm not going to worry about that. We're just going to not skip part B. And then on C, it says based on R squared values, which type of regression is the best. So remember, for best, it's going to be the closest to 1. So then it asks you to list the R squared values for each. So I'll go ahead and do it for quadratic, but I'm not going to make y'all watch me find the R squared values of all of these. But you would go to stat and go to calc. And then quadratic regression is number 5. So I'm going to put 5 in there. And I want to store my equation in Y1. This part, I always do it just so that I make it a habit for myself, the storing Y1. But since you're going to be finding multiple different equations, it's not as important until you know which one is best. But either way, whenever I do quadratic regression, I get that my R squared value is 0.5. So that's what I want to enter there, is 0.5. And then I'm going to go through and fill in the rest of these, and that way y'all don't have to watch the whole thing. So I have all of my R squared values in here, and if you look through these and try to find the one closest to 1, it is overwhelmingly the quartic model. So then it says, write the regression equation for the model of best fit. So I'm going to go back in here and I have quadratic up right now, so I'm going to redo it so that I can do quartic. So I'm just going to go back to stat and then, yeah, calc. And I want a quartic, so that's 7 on this list here. And I want to store that regression equation because I know that's my best one. So I'm going to go to variables, y variables, and put y1 in there. And then I just want to calculate. And I will put this in the notes as well. So my quartic regression model ends up being, sorry, that keeps happening, ends up being y equals a, so 0.02, x to the fourth, and then minus b, so it was negative 1.03, and that's x to the third. C is 15.76, so plus 15.76 x squared, minus 101.86 x cubed, or no, just x, because I've already got my x squared, and then plus 241.19. So that is going to be our regression equation that we're using for all of this. The next thing is estimate the number of seal failures when the temperature is 14 degrees Celsius. So I'm going to come back to my calculator again, and then I'm just going to go to the table. And luckily, the last one and this one are both asking for 14 as our x value. So whenever you look at y, whenever the temperature is 14, you get 0.51 approximately. So for estimating, we're going to say 0.51 failures. And that doesn't look like it says failures. So that would be just an example where you're trying to find the best model. And then the next one is also going to be like that. So this one is the coach is trying to determine if there's even a relationship between how fast players can run and how far they can throw a ball. And so it wants you to record the R-squared values for all of these different models. And we have quadratic, cubic, quartic, exponential, logarithmic, and power. So again, to enter the data, I don't want to know what the kids' names are. I just want to know their times for L1 and their throwing distance for L2. So I'm going to go ahead and enter this data for us. Okay, so now you can see I've got all the data entered, and what it wants me to do is just skip straight to finding R-squared values on this. Just for fun though, I'm going to look at the scatter plot. So I'm going to hit zoom 9. And you can kind of see it's all over the place. But now I'm going to go through and find R-squared values, and I will just pause here and pull it back up when I am done. So we have all of our R-squared values in now. And so our R-squared values are 0.25, 0.308, 0.311, 0.24, 0.25, 0.24. So it still wants to know which one is the best. So technically the best is the one that's closest to 1. So it's going to be quartic. And then it asks, what might the coach conclude about the relationship given these R-squared values? So what I would say for that, since the correlation is so low, and we already looked at the scatter plot and it wasn't like it was all over the place as well. So what we're going to conclude about that is that there is weak or possibly no correlation between the sprint times and the throwing distance of his football team. So that can happen sometimes too, where it throws these numbers at you and then you like it doesn't necessarily correlate. So I just wanted to give an example like that as well. And that was kind of just a mixture of a bunch of different stuff that you could see. So like a couple of new types of regression equations and stuff like that. So it was just some different stuff that I wanted y'all to see. And that pretty much wraps up the best regression models.